So today we're going to finish up the final section of the bonding unit, talking about the VSEPR model. Okay, so VSEPR is basically a 3D arrangement of the atoms in a molecule. And so we use VSEPR, which is called valence shell electron pair repulsion, and it's used to predict the geometries of molecules that are formed from nonmetals. And so it functions under this principle that electron pairs want to be as far apart from each other as possible or repel each other. So, and this is exactly what this is saying, the structure around a given atom is going to be determined principally by minimizing electron pair repulsions. So lone pairs, when you're drawing the Lewis structure, want to be as far away from each other as possible, and so we come up with a 3D arrangement that is going to help do that. Bonding and non-bonding pairs will be as far apart as possible. So let's look at a few examples. So first we have BeCl2, and if we do the Lewis structure, I've already done it for you to save some time, okay, but maybe this would be a good opportunity to pause and double check the Lewis structure with mine, making sure that you are okay doing those. Remember, beryllium's an exception, and so it's going to look linear in structure. So I have one here. Okay, now this is carbon dioxide, but you can see that it's still linear. So linear, 180 degrees. We're keeping these bonded pairs as far away from each other as possible. Okay, and so that's going to give us a linear structure. Okay, the next one is boron trifluoride, and if you do the Lewis structure for that, it looks like this, and again, it is another exception. Okay, and this is what's called trigonal planar. So I don't have boron trifluoride, but I do have this one. Now, this is representing a lone pair, and this is representing a double bond, but you can see that it's all in the same plane, and it's forming like this triangle structure. Okay, and so this would be trigonal planar. So when you draw your Lewis structure, you're drawing in 2 dimensions, but then when we draw the geometry, we want to draw it in 3 dimensions. Well, this is all still in one plane, but we can draw these other atoms as they are actually bonded. Now, once we get into molecular geometry, you don't have to put lone pairs on the non-central atom anymore. Lewis structures would need all of those things. Okay, and so here where we had a degree of 180, whoops, we need a 0. Here, because we have 3 bonds, we're trying to split them as far apart as possible, and so that gives us an angle of 120. Okay, and then we can look at methane, which is CH4. Okay, and so this is what's called tetrahedral. The best arrangement gives a 109.5 degree bond angle. And so the way that we draw this is, now I can hold it for myself, but I'm see if I can hold it for you guys. Okay, I think this would work. So you have 2 that are in the plane. So they are with the plane like this. And then you've got one that's sticking basically out of the plane, and then this one back here that you probably can't see, I'm holding it, is sticking into the plane. And so in order to draw that, because remember when we draw it's 2 dimensions and we need to represent it as 3 dimensions, we have our carbon, we have 1 hydrogen in the plane, a 2nd hydrogen in the plane, and then to draw things that are sticking out of the plane, it's a whole triangle, and then to draw things sticking into the plane, it's what I would call a squiggly triangle. And so this one is the one that's sticking back into the board, this would be the one sticking out at you, and then these 2 would be in the plane. And that's called tetrahedral. So between all 4 of our carbon to hydrogen bonds, we have 109.5 degrees. So basically between all of these, that's our angle. Okay, so to apply the VSEPR model, first you need to draw the Lewis structure. Okay, then you need to count the electron pairs and arrange them in the way that will minimize the repulsion. Okay, and so basically, if you had something like this, anything with 4 bonds around is going to have this structure. Okay, and then, anything with 2 bonds and no lone pairs is going to have this structure. And so it does tend to follow a pattern. So we then determine positions of the atoms from the way the electron pairs are shared. So we're trying to get them as far apart as possible. And then we determine the name of the structure from the positions of the atoms. So, like, this is called tetrahedral, and this one is called linear, and we're going to talk about this one in a second, but this one is called bent. So each structure has its own name, or each geometry. Okay, so let's look at the VSEPR for NH3. So the first thing you would need to do is draw the Lewis structure. Okay, well, nitrogen donates 5 and hydrogen donates 1, so that gives us 8 valence electrons. Nitrogen goes in the center. We have a hydrogen, 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 and I know nitrogen needs 8 to be stable, and so we have 1 lone pair. So that's our first step. Then we count the pairs of electrons and arrange to minimize the repulsions. Well, here we've got 3 bonded pairs and 1 lone pair, and that lone pair is going to take up a lot of space, pushing all those hydrogens down. And so then we determine the position of the atoms, and so because that lone pair is going to push everything down so much, we should get something like that. And then we need to determine the name of the structure, and this is called trigonal pyramidal. And what's actually happening, and I have that one here. Okay, so this is ammonia. Here's our lone pair up top. Okay, if we put the lone pair in the plane and one of the hydrogens in the plane, one is sticking out and one is sticking back. So this resembles tetrahedral, except for tetrahedral there would be an element bonded here, and this is a lone pair, and it does push everything down more. And so if we were going to make this more accurate, our lone pair is in the plane, one of these is in the plane, this one is sticking out of the plane, and this one is sticking into the plane. And so then you're getting this triangle-based pyramid, and that's why it's called trigonal pyramidal. Okay, so let's look at an example. It says determine the molecular structure of water. We know, that water is H2O. Each hydrogen donates 1 valence electron. Oxygen donates 6, so that's 8. So we have our oxygen as our central atom. Hydrogen, hydrogen, so that's 2, 4. Hydrogen's already stable. It can only have 2, so we know we need 2 lone pairs. Then we're going to want to space these as far apart as possible. And what happens is that those lone pairs take up all of this space, and so they push the hydrogens down, and so we get what's called a bent structure. And so that is this one. Okay, so this would be considered bent. And so you've got this angle in between here. Because of those lone pairs that are sticking out, they're pushing the hydrogens down versus something that is linear where it doesn't have any lone pairs. And so lone pairs really make the difference when you're talking about molecular geometry. Okay, so let's talk a little bit about those lone pairs. So as we said, shape is determined by lone pairs. If water didn't have lone pairs, it would be linear, like we looked at, not bent. And so it would also have no polar bonds and no dipole moment. And so lone pairs require more space than bonding pairs. And as the number of lone pairs increases, the bonding pairs are going to get more squeezed together. So when we looked at water, we had 2 lone pairs that really squeezed these down. When we look at ammonia, we only had 1 lone pair. It didn't squeeze the hydrogens together as much. Oops. Okay. Okay, so here's a general chart of molecular geometries based on the number of electron pairs that you have. This would be assuming that there are no lone pairs. Okay, and so this would be no lone pairs, all bonded pairs. Okay, so here, technically, we have 2 bonds, even though we have double bonds, and so this, this would count as linear. Okay, once we get into some lone pairs, the geometry will change a little bit. So no lone pairs would be something like tetrahedral. Okay, and then if we had 1 lone pair, we're going to trigonal pyramidal, and 2 lone pairs, we're going to go to bent. Okay, and then we can also have different structures based on the number of lone pairs and bonds. So for 4 electron pairs, these are going to be your progressive shapes. So none, 1, and 2. And then for 5 electron pairs, so these would be exceptions. Okay, we're going to go from trigonal bipyramidal to seesaw to T-structure and then to linear. So this linear one, you would have some element, and then basically around that central, you would have these 3 lone pairs like forming a circle, and then your 2 elements around like that. Okay, so let's look at another example, this time with exceptions. Okay, so for PCl5, let's see, phosphorus donates 5, each chlorine donates 7, and so that gives us 40. And so we know phosphorus is in the center, and we have 5 chlorines. Well, 5 and no lone pairs is trigonal bipyramidal. And so we get 5 chlorines. So trigonal bipyramidal. Okay, if we go to PCl4, now we have 5 plus 4 times 7. So that should give us what? 30. Okay, so that should give us 33, but this is a plus 1 ion, so we subtract 1, so that gives us 32. So we have phosphorus, chlorine, 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 chlorine. Now, when we are doing Lewis structures and molecular geometry for ions, we need the bracket with the charge. Here we have no lone pairs and 4, and so this would be tetrahedral. And if we want to draw it correctly, we would have one of the chlorines sticking out of the plane and one of the chlorines sticking back into the plane. And then if we look at PCl6 minus, we know we have 5 from phosphorus, plus 6 from chlorine, plus 1 because of that negative, and that should give us 48. And so we have phosphorus and then 6 chlorines. Oop, I didn't space those very well. And so because we have 6 bonds and no lone pairs, this is what's called octahedral. Brackets and then the charge. Okay, so a lot of these is just knowing how many bonded pairs, knowing how many lone pairs, and then knowing the shapes. Some of them are going to be pretty familiar, like tetrahedral, bent, linear, trigonal, pyramidal, trigonal planar. Those you should know. Alright, let's take a look at another example. So we want to predict the structure of xenon tetrafluoride and whether it has a dipole moment. Okay, xenon donates 8, each fluorine donates 7, and so that gives us 36. Excuse me. So we have xenon in the center, fluorine, a fluorine, a fluorine, fluorine. If we do all the electrons around each of the fluorines, we should end up at 32. And so xenon can be one of those exceptions, so it's got 2 lone pairs. Now because it has lone pairs, those want as much space as possible. They want to be as far apart from each other as possible. Well, the best arrangement is to put them at opposite ends. And so basically what happens is that then you have these 4 fluorines that are kind of orbiting around the center of the xenon in a ring. So we have 2 sticking out of the page and 2 sticking into the page, so forming this ring, and then you have the lone pairs on top and bottom. And this is called square planar. It's forming like that square. Okay. Oh, whoops, we needed to talk about dipole. Okay, so when we look at dipole, we talked about the polarity of a bond, but we need to also talk about the polarity of the molecule, and you need to think about it like tug of war. If all the bond polarities cancel, then there's no dipole moment for the structure. But if the bond polarities don't cancel, then you have a dipole moment. Now, because we have all 4 of these fluorines and they're all pulling at the same angle, okay, they're all going to cancel. And so then you have that lone pair on top and bottom. So I would say in this case, we have no dipole moment. Okay, but if we look at something like water, okay, water's more electronegative, so it gets the partial negative. And that means that we have dipoles going towards the oxygen. So now, bond polarities. Dipole applies to the molecule. So we have these polarities both going towards the oxygen. Those aren't going to cancel. They're going in one direction, and that's due to the lone pairs pushing those hydrogens out of the way. And so now we have a dipole moment in that direction. Okay, so if we look at NO3, oh shoot, that minus should be up here, -1. NO3 1- has 3 resonance structures, and they are all planar with 120-degree bond angles. So we'll draw it for you real quick. You should have an oxygen, and another one. And so basically, the resonance could switch to the double bond being on this oxygen or this oxygen. But they're all going to have the same geometry, so they're all planar with 120-degree bond angles. So for the VSEPR model, multiple bonds will count as one electron pair. So we talked earlier about CO2, and this counts as one bonding site, and this counts as one bonding site, so that's kind of how I look at them. And so this would be considered 2 bonding sites total, which is linear. And so we're going to count multiple bonds as one pair. And we can use any resonance structure to predict the geometry of the structure. Okay, so we want to predict the molecular structure of sulfur dioxide, and then is it expected to have a dipole moment? Okay, so sulfur dioxide is SO2. We know that sulfur and oxygen donate 6 valence electrons, and so that gives us 18. Sulfur is going to be in the center, and so if we give everything single bonds and satisfy the octet rule, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We have too many, so that means we need to share, so I'm going to take this pair and have them share instead. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18. So that works. Then we need to do electronegativity. I'm thinking oxygen is more electronegative without looking at a periodic table to see the trend, but I think oxygen is more electronegative. So that means we have a polarity this direction for one of the oxygens and this direction for the other oxygen. Even though we have a double bond there, because it's sulfur to oxygen, that amount of pull is the same, and so we would say no dipole moment, even though we do have polar bonds. Okay, so whenever you have an electronegativity difference, that's a polar bond. But it's if those polarities don't cancel, that you have a dipole moment. Okay, sometimes you're going to have molecules with no single central atom. And so you're going to predict based on, for this one, pairs around the carbon and the oxygen atom. And so we're going to have carbon, hydrogen, 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 oxygen, hydrogen. And so I've got that one. It looks like this. Now really, I would more look at the carbon, but technically these are both our central atom. And so we need to look at both of them. So carbon has 4 electron pairs around it, right? So if we held carbon like this, maybe, then that would be tetrahedral. Here's 1, 2, 3, 4 bonding sites. Okay, if we look at oxygen, it's got 2 lone pairs here, so let me draw those on. And so technically this is also tetrahedral. But the only problem is that it gets slightly distorted by the space requirements for those 2 lone pairs that are on oxygen. We've got almost a bent shape going on with those 2 pairs there. And so that can be a little tricky. Okay, there are some issues with some compounds when it comes to the VSEPR model. And in order to deal with all those issues, we would have to add more rules, but we try to keep it simple. And so even, this simple model will have exceptions, but it does apply to most models. Okay, so remember, you need to first determine the Lewis structure. Then for molecules with resonance, any of the structures can be used to predict geometry. You sum the electron pairs around that central atom. This is where the central atom becomes really important. And then count each multiple bond as a single pair, single bonding site. And then use the chart to find the arrangement that minimizes electron pair repulsions. Now, when it comes to the test, you are going to have to know the standard ones. Tetrahedral, linear, bent, trigonal, planar, those. And so the more practice you do with them, the more you'll see the patterns, and those will just kind of become part of your chemistry knowledge. Okay, remember, lone pairs require more space than bonded pairs, and at angles of less than 120, lone pairs are going to produce a slight distortion in the shape. Okay, so again, before we get started with our check for understanding questions, here's another chemistry cat joke. Different cat this time, we're mixing it up a little bit. Okay, so let's move on to our checks for understanding for section 6, which talked about valence shell electron pair repulsion theory. Okay, so number 1, what about electron pairs determines the molecular structure? And how does this relate to the formation of different shapes like trigonal, planar, and tetrahedral? Number 2, summarize the steps to apply the VSEPR model. Number 3, what is the significance of having lone pairs on the central atom? And number 4, how does molecule geometry influence molecule polarity? Okay, so give these a try, and we'll discuss them in class. Have a good day.